So here is a quantity discount problem where we have annual demand, ordering cost, and the carrying cost or holding cost is given as 25% of the cost of the item. And here is the price break including discounts. Okay. So to develop the EOQ here, we have to compute the optimum quantity for each price break, and we have to follow a rule for this. So quantity discount problem. Rules for developing, we'll call this candidate Q. These are the candidates for EOQ, right? Candidate Q for each price break. Okay. Now we're going to use some notations. Okay. Let LL equal to lower limit for the quantity range for a given price break, like the lower limit, okay, for each price break. And let's use UL as the upper limit for the quantity range for a given price break. So that would be the right hand side. So in the last case there is no upper limit, and Q is the quantity using the EOQ formula for a given price break. This will be slightly different because your holding cost is going to be 25% of the price per unit. So your holding cost will be slightly different in each of these three cases. So when you use the EOQ formula, square root of 2 times D times S over H, the Q will be slightly different in each of those cases. Okay. So for a given price break, now you compute Q, then there are three possibilities. The Q may fall below the lower limit, or the Q will be between the lower and the upper limits, or Q will be above the upper limit. Okay. So how do we deal with developing your candidate Q in each of those three cases? So we'll start with Q being above the upper limit. So if Q is greater than the upper limit, then we can just ignore this price break. So even for a smaller quantity, we can get the better price. So there is no need to worry about this price break at all. If it is in between the lower limit and the upper limit, so that means this quantity is valid for the range, then candidate Q is Q itself. There is no change. You keep that Q as is. Now if Q is less than lower limit, then you have to ignore Q. Candidate Q will become the lower limit. So the lower limit is taken as the candidate Q. So that's what we're going to do now for this problem. So here we are given D is 5,000, S is 100. Now H is 25% of P, where P is price per unit. So we start with step 1. Develop candidate Q for each price break. So that's our step 1. So we have the Q range. So the first one is 1 to 149. The price for that range is $80 a unit. Now holding cost is 25% of P, so this will be 0.25 times $80, so that's equal to 20. Then we compute Q, which is that. So now use 2 times 5,000 times 100 divided by 20, and that is equal to 224. Okay. Now we have to apply the rule, okay, this A, B and C rule. So here the lower limit is 1, upper limit is 149. Now our Q is greater than upper limit. So this is the first case, in which case we ignore that price break. So 224 is greater than upper limit, so we ignore. So we're not going to consider that price break. Next price break is 150 till 399. The price here is $70. So 0.25 times 70, our holding cost is $17.50. So then EOQ formula is, now instead of 20 we are going to use 1750, and this is 239. And now the lower limit is 150, upper limit is 399. Okay, so 239 is between the lower limit and the upper limit, so candidate Q is 239. Okay, the next is 400 and above. $68 is the price. So 0.25 times 68 is $17. So 2 times 5,000 times 100 over 17 is 243. The lower limit is 400. No upper limit here. Okay, it's kind of getting messy. Let me. So no upper limit. So since 243 is less than the upper limit, so this is the third case. It's less than the upper limit. I'm sorry, less than the lower limits. Here the third case, Q is less than the lower limit. So Q should be the lower limit. The candidate Q is the lower limit, which is 400. So now we have the candidates. There are two candidates here. We have to ignore the first one. And then Q equal to 239 is one candidate. Q equal to 400 is the second candidate.